Okay.
Hello everyone. So let me welcome Professor Nicolas Fang from the Department of Mechanical Engineering at the Massachusetts Institute of Technology. So Professor Fang is a famous physicist and mechanical engineer working on acoustic, electromagnetic and mechanical metamaterials, and today is going to talk about acoustic metamaterials with broadband tunable impedance matching. Professor Fang.
Thank you so much, Sebastian, for the great introduction. And I really want to thank organizers, Sebastian, Bogdan, and Muammer, for this great opportunity to talk to you about our ongoing research in the direction of broadband tunable impedance matching using acoustic metamaterials. So good afternoon, good morning, or good evening, depending on where you are. Today, I'm going to give you some of our ongoing research projects and in particular some of the ongoing collaborative efforts with different research groups. So before that, let me make sure that I acknowledge different collaborators, different field expertise, material scientists, mathematicians, mechanical engineers, chemists, without whom some of the research activities would not be possible. And I'd like to also give credit to students and postdoc, as well as the former members from the group who really made all of this great research effort that built together my talk today. And last but not least, the different funding agencies as well as industrial supporters, to provide the financial support for the research effort and activities. So my group at MIT, as Sebastian just introduced to you, work on physics and applications of different metamaterials, optical, acoustic, as well as mechanical metamaterials. On one end, we are looking at the fundamental limits that really constrain or provide the principles for concentration of light and sound down to the for example monolayer or even atomic layer signals. And we look at what are the processes that dictate the production, propagation, as well as absorption and conversion of those elementary photon and phonon energy. And in order to do so, we build fabrication tools that integrate different micro nano structures, as well as assembly of different dissimilar materials, polymers, metals, nanoparticles of magnetic actuation, and so on and so forth, so that we will be able to explore and expand the library of metamaterial and metastructures to drive different efforts, for example, to extract light and provide more efficient solid lighting devices, or to provide more compact and efficient sound absorbing materials. So today I'm going to just focus on our effort in terms of sound, and in particular the impedance matching with sound materials. And why this is an important direction, let me give you a short background with some ongoing case studies, and if time allows, I will also share some discussion and reflection of our research in this end. So if we look at the history of acoustic devices from year 1940 to 2020, you may be really fascinated by the continuous miniaturization of microphones. Back in the 40s, we were talking about still some of those electric devices that are of the order of tens of centimeters in say width. And today, if you look at the integrated microphone, for example, in your cell phone or say embedded on your computer, then they are now at the size that are or volume that are 1,000 times smaller, or even say approaching to say the size of or smaller than for example a needle head. So this apparently seem to go in parallel with the familiar or famous Moore's law that drives the revolution of electronic devices. But can this trend be applied to more broader devices in the acoustic and ultrasound domain? We see that at least for the case of underwater acoustics, this seems to be not yet feasible. For example, today, if you are trying to conduct a underwater survey to plot, for example, the sand and oil field for the off-shelf distribution, then very often we resort on a very noisy device such as the air gun. And those air guns are actually emitting compressed air at a high pressure. And by doing so, it generates a very large actually noise or at a high intensity level. So on the bottom, you see that for the noise level of a seismic gun, it goes something close to 220 dBs of above, for example, the absolute pressure, and this is actually detrimental to many of the wildlife, turtles, the whales, as well as dolphins, who relies on the acoustics or underwater ultrasound as means for communication, navigation, or defense. So why this underwater ultrasound emission is difficult to scale? It is not as say efficient or compact to the size of micro devices in the airborne scale. So one outstanding challenge that we see is that to enable substantial acoustic gain, the scale actually works against us. If we take an analogy of, for example, the size of an antenna, you see that for a sub-wavelength structure feature of, for example, acoustic length A, then the efficiency of such an antenna to emit into the free space will be inversely proportional to the wavelength to the fourth power. Similarly, if you define a acoustic gain, then for the smaller devices, then we will also see a similar demanding constraint that sets, for example, the limit of accessible mechanical impedance. Over here, let's take for example, a famous perforated sheet with sub-wavelength holes. Then its impedance defined as the complex ratio of the pressure or force per unit area versus that of say particle flow velocity. Then we see that the both resistance as well as acoustic reactance scales inversely with the size of the perforated holes. So this actually has a direct impact to how efficiently one can generate and detect sound if we wanted to match, for example, the impedance of the environment or ambient materials. So I think that actually can really kind of say date back to the important studies widely applied to many different fields, both mechanical, acoustic, optical field actually learn a lot from the earlier discoveries that set the stringent requirement of impedance matching. A very common solution, for example, is to use a quarter wave plate or some kind of anti-reflection material. And by doing so, we often see that such a layered, so to speak, anti-reflection coating or back panel actually set up by a stringent, say, length scale. This is comparable to a quarter wavelength. And for airborne sound, for example, at 1,700 hertz, we're looking at a thickness of at least 5 centimeters. If you are not 5 centimeters away from, for example, the solid back panel, then you will be suffering, for example, of the energy coupling to the sideways. So this is actually well known as a quarter wavelength relationship for the fundamental transmission that results in the narrowband matching devices. So how do we overcome a problem like this? Hello? I see there's a question from the chat channel.
All is fine, Nicolas. All is fine.
Okay, great. Thank you. All right. So with that in mind, I just wanted to also properly provide a context that we enjoyed so far. Being an optical engineer, we enjoyed so far a lot of the analogies between acoustics as well and electromagnetism. In fact, some of the concepts are really beautifully elaborated by a former group member, Navid Nemadi, who come from the Dennis Lafarge group. Over here, we see that in this particular analogy between electromagnetism and acoustics, we can beautifully translate the concept of electromagnetic devices and materials now and map it to many fascinating acoustic effects and concepts. In particular, the closest match to permittivity and permeability will be the dynamic compressibility as well as the dynamic density. And in order to now find the candidates, for example, for acoustic impedance matching, then it calls to look into, for example, the available space of engineered as well as natural materials. For example, on the top right, we see the famous Ashby chart, which plots the material density as well as the available modulus or comparable to Lamy constant, for example. And on this chart, we see that most of naturally occurring materials and the engineered materials actually are located in a very narrow island in the first quadrant. So for acoustics, for example, we are looking at the slope that dictates, for example, the ratio between modulus and density, which give you the speed of sound. And on the other hand, if we are looking at acoustic impedance, then we can draw another set of diagonal lines, as shown in green, where you can start to see, for example, how different materials actually changes their acoustic impedance by order of magnitude from, for example, the very hard and stiff solid materials to very lightweight and porous foams. So unfortunately, if we are just going to find the intersection, for example, of the speed of sound as well as the impedance, we have now limited choices. For example, to match off that of impedance of water, you may only have a few cases like the honeycombs or bubbly fluid or bubbly foams, as we heard from previous speakers in this seminar series. So how do we actually conquer the, so to speak, unmet white space? Then both, I would say, like structured materials as well as now self-assembled the foams and lattices may potentially meet this demand. And back in, say, 2014, we reported that you could potentially generate octet truss-like lattice structures that could be, say, as stiff as engineered rubbers, but yet with a, say, density that is tunable from, for example, close to the aerogel all the way to something that's comparable to, for example, hydrogel materials or fluid. So if we further expand the material space, then we may be able to even go to different quadrants, adding resonance effects, offering, for example, the possibilities for acoustic focusing to, say, tailor the dynamic effect, including the now popular idea of negative density, negative modulus, and even including the space of, say, anisotropy and inhomogeneity that can lead to, for example, acoustic bending in a curved space. So, but I wanted to offer a slightly different perspective that potentially would enhance our capabilities to, say, change the impedance from the hard materials to the soft materials. And this is actually abundant with, say, examples such as jellyfish or moth scales. In both cases, those tissues forming for example, the skin or the muscles of jellyfish are actually soft, elastic, and as a result, they actually also can sustain a very substantial concentration of water. And if you had a chance to, for example, put a jellyfish under a ultrasound echo sounder, you find that it is nearly transparent to the environment, generating very weak echoes. So this makes jellyfish very hard to detect, actually, under the underwater acoustic signal. In contrast, so far, what we have built in the labs using, for example, aluminum or hard plastics, they actually have rigid walls. They have difficulty to match with the impedance of that of water or soft tissue. So some of the structures and shapes are fixed once they are fabricated, and this is difficult to tune. So we talked to different colleagues of experience of material science, and fortunately, say in the past 20 years or so, the field of hydrogel actually is emerging as a very promising acoustic material. So on the right-hand side, I'm showing you some early demonstration of Professor Zhigang Sou's group at Harvard, for example, to create a transparent acoustic speaker, a loudspeaker that can be seen through and of a very low form factor. And in addition, the hydrogels also start to demonstrate some very promising abilities, for example, to survive under large deformation and promote adhesion between dissimilar materials. So all of those promising factors and the near perfect acoustic impedance with that of water is triggering us to take a closer look of those materials. So some of our earlier efforts was led by Professor Qiming Wang, who is now a rising star at the University of South California. And during his postdoc period in my group, he initiated the effects of doping the hydrogel and other soft elastomers by, for example, mixing magnetic nanoparticles into the gel materials. And by doing so, we find some very kind of surprising effects. Creating a, say, octet-truss lattice, for example, as shown on the top right, by mixing the magnetic nanoparticles, such as, I think, ferrous particles that are, or ferromagnetic nanoparticles, we can now use a very small magnetic field, external magnetic field of down to 200 Gauss, is sufficient to compress the lattice from the relaxed state to nearly 50% of compression. And by doing so, you can see that the lattice undergo an immediate change of the pore fraction and even some of the topology of the connected network. And as a result of that, the transmitted sound is experiencing a strong modulation as a function of this compression. So at the relaxed state, you can see that this octet-truss is forming a very nice band gap at the frequency of 3,000 to 5,000 Hertz, and yet, say, a compression, say, to 50% of strain will now, say, create a newly generated, say, defect modes that allows the sound to transmit through, for example, center frequency close to 3.5 or to 4,000 Hertz. And this actually can lead to more exotic states related to, for example, the tunable density as well as modulus. And this is actually superior compared to the earlier counterparts. If you actually also had experience playing with ferrofluids that similarly also can be driven by external magnetic field, you probably will notice that here we're talking about a order of magnitude difference in terms of acoustic impedance. So the opening and closure of the band gap actually is not possible if you were only say placing those say ferromagnetic particles, for example, and form a liquid suspension of them. And say fast rolling in terms of time, we are also fascinated to see that the hydrogels actually could also create a synergistic effect because of this its optical transparency. In 2017, together with Professor Xuanhe Zhao's group, we reported that a soft elastomeric say actuator formed by this tough hydrogel actually can lead to nearly 90% of light transmission, as well as say less than 5% of say acoustic impedance mismatch, as shown on this medium column. So the overall reflection measured from, for example, a sample that's of a centimeter thickness will be less than 2% in most of frequencies of interest. And triggered by this, say, two young colleagues, Professor Kai Zhang, who took a visit and spent a year at MIT, worked with my former student, Dr. Chu Ma, who is now an assistant professor at the University of Washington at Medicine. They are looking to the possibilities to inject different fluid, gas, liquid metal, or other, fluid of tunable density into this hydrogel structure. This can be done completely pneumatically. And here I'm showing you that the liquid metal is purged through individual channels formed in the hydrogel materials. And this is feasible by say a programmable manner, meaning that you can fill individual channels and leave, for example, adjacent channels now completely unfilled. And by doing so, they find that this hydrogel sheet actually can have a very broad range of acoustic impedance. You can change the impedance almost 3 orders of magnitude at the frequency between 50,000 to 150,000 kilohertz. And this has been experimentally validated. On the top panels, you see that individual channels that are filled with liquid will appear now transparent, and those that are filled with air actually remain of a strong reflection. So you can see that how many channels are being filled in different cases between panels A to C. And this individual channels that are embedded in the hydrogel sheets can be made with sub-millimeter scale of diameter and very long, centimeter long channel lengths. And by doing so, experimentally, you can see that the completely filled hydrogel sheet will enable nearly 100% of transmission. And by selectively filling the channels, for example, from 1:1 to say 1:8 ratio, now it is possible to decrease the auto transmission by a factor of 2 to 5. So this is in fact also being supported by the force wave computational models as shown on the right. And so such a thin sheet of hydrogel material with now tunable channels actually offers a very exciting opportunity. On the left-hand side, we see that for engineering materials or typically for impedance matching fluid, very often you have to look into, for example, a very specific range of impedance corresponding, for example, for air, fluid, or solid. Here, we show that if you are able to inject, for example, water or a liquid metal, then it is possible to cover a impedance range by 3 orders of magnitude. And by doing so, together with the broadband nature of this hydrogel sheet, we see that it is possible to create a tunable filter, as shown in the right-hand side, that at the pumped state will allow ultrasound signal to transmit through without substantial reflection. And when it is purged with air fluid, for example, then those channels that are filled with air will block the incoming sound and leaving a selective window. So this is almost now the acoustic version of an optical grating, but with now a tunable solid loading or the filling ratio. So this is opening up more exciting explorations, for example, to design and filter the ultrasound image processing, and some of the research effort is going on, and I wish I'll be able to show you more when we have more concrete experimental results. Now let me switch gear and talk about our earlier cases of animals, in particular wildlife, who uses biosonars to navigate to in this case to chase fish. Here, please bear with me if my video is a little bit loud. So this is actually a drone image or video captured on shallow water, illustrating. Let me turn off this sound. I think we can neglect the sound part. Just watch how the dolphin is playing around in the shallow water at first, and now him or her just got excited for a fish. So, so this is the chasing part. You can see that the first few, let's say, attempts was unsuccessful, but dolphin was quite persistent in this case, and continued to follow the fish for quite a few actually cycles. So how can this be done with a biosonar? I will not play the rest of the video because it takes 3 minutes actually to finish that. But I think the dolphin actually had the fish at for a snack. All right, so let me now get back to a collaborative effort that was made possible thanks to Professor Yu Zhang of the Department of Ocean Science from Xiamen University. Professor Zhang actually come to MIT for his sabbatical year, and that's because of him we learned a lot of how acoustic metamaterials can be inspired by natural or biological systems. Here, in the first example, we show a finless porpoise, a sibling or a close say adjacent of a dolphin, also has a acoustic mallet lens. In this case, Professor Zhang's group was able to reconstruct the forehead of the finless porpoise, and here we highlight the acoustic properties reconstructed from this forehead, with in particular the speed of sound measured from melon muscle as well as the other connective tissues. You can see that the sound velocity actually changed by a factor of 50, say by more than 50%. And why this is important? It turns out that the beaming effect is a synergistic process that incorporates both the hard tissue, bones, and skull, as well as the mallet lens and other connective tissue. Here, by modeling those soft tissues with now a metamaterial, say using, for example, steel cylinder array of tunable filling fractions, we're able actually to emit a broadband click from the back of the forehead or the phantom, and by doing so, in the computational results, we see that it is possible to generate let's say, directed beam oriented at 58 degree with a beam width close to 18 degrees. So this is actually very close to the computational results obtained from the full-scale biosonar model of the porpoise. The estimated angle and beam width are also quite comparable to the acoustic metamaterial, say, built phantoms. So for more details, you're welcome to read our description of the computation and the experiments in this particular paper publishing back in 2019. And with that, we also expanded the process to another precious species, the humpback dolphin, that was captured back in year 2015 in Quanzhou waters. That was actually at the proximity of Xiamen city. So Professor Zhang's group was able to reconstruct now this particular set of forehead using the micro-CT images. And because of the high resolution of the micro-CT setup they have, it is possible to also deduce the specific density of individual tissue and measure, for example, the sound speed in a layered fashion. And by doing so, we actually come to a particular hypothesis. Can this three-dimensional complex acoustic emitter be modeled by a non-uniform transmission line, which is a reduced order picture? And as a first attempt, we look into a one-dimensional acoustic impedance distribution. So here, the dotted points are actually the data obtained by the acoustic impedance reconstructed from the forehead. And the red curve or the dotted line actually is fitting to a one-dimensional gradient model. And by doing so, we can plug this impedance as a function of distance from the transmitter to the ambient environment here, water in our case, by forming a set of layered metamaterials. And the solution of sound propagation actually can be analytically obtained thanks to the earlier pioneer work published back in 1946. And here we are able to solve, for example, the effect of inhomogeneous impedance distribution to the resulting reflection of the composite material. And in order to construct this particular Metagel, we also applied the effective medium theory with long wavelength approximation. We heard of many pioneer talks earlier this semester in this seminar series. And what's most interesting to us is that there is a very broad range of the density as well as the modulus between, for example, hydrogel and that of steel. One can tune simply by this mixing rule of the effective medium story. And as a result, you can see that such broadband transformer containing the gradient structure is really overcoming the narrowband frequency limit that I introduced to you earlier using the quarter plate process. So yeah, on the bottom, what I'm showing you is the computational results for the quarter wave wave impedance matching layer, which shows a series of spikes. Each of them contains a narrow resonance peak, and the bandwidth of each peak will be only close to 5 kilohertz. In contrast, for a layer of 2.5 centimeters, you can see that the red circles indicate that you are able to, red circles indicate that you are able to, say, obtain near uniform transmission for almost 180 kilohertz of frequency band of width of interest. So this is actually a very fascinating observation or prediction from the computational results. And experimentally, indeed, we are able to validate the prediction by assembling the composite material, which contains an array of the steel cylinders that are embedded by the, the hydrogels. In this case, we used a argos with only 3% of the solid loading. And you can see that the red solid circles, circles represent the experimental observation where the transmission is nearly uniform uniformly above 50% of transmission for all of the data collected from, say, 50 to 230 kilohertz. And this is a very good agreement with the experimental, the computational predictions that we obtained earlier. And there is a very clear contrast to that of a quarter wave, say, backing layer, which only give you a narrow resonance peak for both layer thickness of 2.5 and 1.5 centimeters. And why this is fascinating, in the earlier case, I was telling you the challenges that we're facing in terms of echo sounding, or ranging measurements. Here, to illustrate the difference, let's consider 3 different scenarios. In this 3 scenarios, we placed 2 scatterers. One is an iron cylinder. You can consider this as a mock model of the fish in the near neighbor. And on the background, we also have a steel wall that is generating reflection. This is placed at a distance of 80 centimeters. So let's compare the 3 different scenarios. The first case is a simple scenario that the cylinder was not present, and what we hear is primarily the reflection from the wall. So both quarter wave plate as well as the broadband echo standards provide nearly equal signal to noise ratio. But since are drastically different, if you have a cylinder in the near field, or I'm sorry, in the 30 centimeter distance, then we see that it is difficult to measure or say to detect the wall for the immobile cylinder. So if you have a obstacle right in front of you, you may have, there is a big chance that you miss another obstacle that are just slightly behind. This is what happens when you have a narrow bandwidth echo location in place. And when the object is moving, for example, a swing cylinder is placed, you start to hear the reflection from the wall, but you start to miss the moving object in the nearest neighbor. So that's actually the challenge we also have now for this narrowband echolocation process. In contrast, the echo sounder that are coupled with this broadband Metagel actually were able to provide very distinguishable time distance reflection signals, both in the case of the immobile as well as the swaying cylinders. We can clearly separate the reflection from the cylinder as well as the steel wall. So this actually justifies the advantage of having a directional and broadband signal coupling to the echo sound. So with that, I wanted to provide a quick summary of what I presented to you so far. First of all, we see there's an exciting opportunity to use soft materials and hydrogels in particular as a new forming block or building block for acoustic metamaterials. In the first example, I hope I convinced you that the hydrogel actually offers new opportunities to tune, for example, the acoustic impedance and by 3 orders of magnitude from, for example, approaching to the air fluid and all the way to now that of the density of common metals. And in the second example, we were looking at the impedance distribution from a metal lens or more complex forehead of porpoise and dolphin, and we showed that by adapting those impedance distributions, we are able to generate a different set of broadband transformers, which overcomes the narrow frequency limit that was originally set forth by the quarter wave plate design. So there are many ongoing activities that will further advance our studies that couples, for example, acoustic waves from a broad angle, broad frequency, as well as broad impedance matching requirements. Here, I'm just going to quickly point out to some ongoing effort here. This first one is in collaboration with Professor Yun Lai's group and Professor Johan Christensen, in which we look at the opportunities to transform, for example, the Faraday cage, which are originated from electromagnetic signal noise insulation, and by now plotting a possibility for a 3-dimensional acoustic cage. Thanks to Dr. Cheng-Tai Liu, who were a visiting student and spent a year with us at MIT. Cheng-Tai and Chu collaborated together to evaluate the possibility, for example, to block the some noise without actually impeding, for example, the airflow using an open-ended lattice structure. And what we found very nicely is that so this meta cage is even robust against say modest airflow conditions, for example, by placing a fan next to it. And it turns out that the secret that we are able to enjoy was coming from this space calling tunnels that enables, for example, acoustic impedance matching now at a thin layered structure as well, while maintaining a open aperture that remain effective, for example, for airflow through the cage. And last but not least, I think the impedance matching concept can be applied to a much broader domains of airborne sound and ultrasound field. Thanks to the mobility grant support, as well as the external collaboration opportunity with a group at European Union. We are fortunate to have different opportunities to collaborate with Dr. Jesus Martin, looking at sound absorption with now more compact and efficient designs, as well as the reproducible case of the periodical power structures using different additive manufacturing technologies. I just wanted to wrap here, but if you have any questions during the Q&A, I'm happy to elaborate more details. With that, thank you very much for your attention, and once again, thank you for the organizers for the exciting opportunities to discuss and present our research.
Thank you very much, Professor Fang, for this exciting talk. So now I would welcome any questions related to your talk or earlier research you've performed. So please, people, come forward with your questions.